Bismillahirrahmanirrahim. So in this lecture we are going to be talking about regression trees. In the last lecture we looked at decision trees, and the difference between the two is that in decision trees we are trying to predict the labels corresponding to different data, and in the case of regression tree we are trying to fit real valued outcomes. So the difference between them is that in a decision tree, at the leaf node you are going to have a category such as a yes or a no, or maybe cats and dogs and horses and categories of something, while in the regression tree we are going to have real valued outputs. For instance, stock exchange, the prediction of a stock exchange. For instance, the value of a foreign currency. For instance, the number of hours that I need to work per week, and stuff like that. So in the case of a regression tree, what we need is a real valued output, and the input also for regression trees can be very different in terms of the nature of the attribute than that of a simple decision tree. So in this lecture we are going to look at what regression trees are, how to interpret a regression tree, and then how to build our own regression tree. And just like for the decision tree, we are going to look at which attribute to choose, where to split on that attribute, and how to make that real valued prediction instead of the simple category. So we'll start with a few examples, and I prefer using a visual or an example based approach rather than just a pure mathematical one. I think it's easier to follow and it's easier to understand. So let's take a look at this data. In this case, we can see that this on the x-axis is the number of hours worked per week, and on the y-axis we have the productivity, or in terms of the total percentage of tasks that you can accomplish. So naturally, the more you work, the higher the tasks you can achieve. So the productivity will be higher, and the lower the number of hours worked, the lower will be the productivity. So this is an example of a linear data. We call it a linear data because for two reasons. First, you can fit a straight line to go through it. For instance, like this. So this is a straight line. It's not a perfect match, but it gives you the general trend of the data points. And secondly, the interpretation is that there is a monotonic way in this data is behaving. So monotonic, going in one direction. As the numbers of hours are increasing, the productivity is also increasing. There is no curve inside this data. It doesn't say that the productivity will go, let's say, up to 30 weeks and then start lowering. So it doesn't work that way. So this is an example of a linear data. So for a linear data, we can fit a line. It's pretty easy to do that mathematically. You can fit either a regression line, or you can simply just sum of squared error and fit a trend line. And it's very easy in almost all tools, including in Microsoft Excel. You can just fit a trend line into this data. You can even guess it. It's just a simple. There are two attributes. There's nothing much to it. You can have a pretty good guess as well. It may not be mathematically accurate, because a mathematically accurate line is one that minimizes the sum of the errors from the different points. So if you fit one by hand, or just by looking at it, it may give you a good idea, but it will not be mathematically very accurate. However, suppose now that we look at another kind of data, and that is the non-linear data. So in the non-linear data, we have a different kind of trend. So we see that as the number of hours are increased, the productivity is increasing, and then it reaches a maximum 100% productivity around maybe 17 to 23 or 24 hours per week, and then it starts declining again. So in this case, if I want to set a regression line or a trend line, this is not going to be a very good fit. For instance, and there's also going to be a question of which line is the best representative, or if any of them is a good representative at all. So this is the first example that I can use. This is an example of trend line. This is another line that I can fit, and this is a third line. So the first question is which one of them is good, and the second question is any of them good at all. Instead of doing that, what I can do is that I can also fit in what we call a regression tree. So this is where the regression tree comes. If you look at this data, so I want to make this prediction, and the prediction was very simple. For instance, in the case of a trend line, the meaning of this was that, for instance, if I use this red line, and this means that if at any point I can make a prediction that if I put 11 hours of work in this week, I am going to maybe get, let's say, 26% productivity. So you can use this trend line to make this kind of prediction. So you need to do the same with this regression tree, and we'll look how the regression tree is interpreted before we look into how we make our own regression tree. So what this is saying is that the hours worked, or the x-axis, was the attribute that we chose, and we take it as a node, and then we split on this node. So if the hours worked is less than 14.5, then we say that if the answer to this question is, so this is a question, hours worked less than 14.5, yes or no. If it's a yes, we say you're going to achieve a 4.2% accuracy or efficiency, sorry. And if the answer is no, then you are going to have another question to ask, so whether the hours worked was greater than 29, and if the answer was yes, I haven't labeled it over here, but the general convention we will be using in this lecture is that the yes are the left sides and the no are the right sides. So if the answer to this question is yes, I get a 2.5% efficiency, and if the answer is no, I need to ask a further question, and that will be if that the hours worked is greater than 23.5, and then again if it's a yes, I get this answer, and if it's a no, I get this answer. So this is fairly easy and very visually appealing to understand the data, and we'll see how the interpretation is, what part of the data is this part representing. So in this slide, what we can do is we are going to find a mapping between this tree and this data. So if we look at this 4.2% efficiency, so hour worked less than 14.5, let me draw where I think this 14.5 line is. So this is going to be somewhere around this place. So it's going to look something like this. So it's not a straight line, but we are going to assume it's a straight line. So this is the first part, and let's draw another line over here. This is the second line, and this is a third line. So approximately we can see that we have 4 different divisions. So this is the first division, this is the second division, this is the third, and this is the fourth, or 4 different parts if you like. So what is this 4.2% efficiency referring to? If you look here, since hours work is on our x-axis, if we say that the hours work is less than 14.5, so assuming this is 14.5, so this is this should be over here. So assume this is 29, ideally it should be somewhere over here, and then this is 23.5. So if the hours work is less than 14, it means we are talking about this region. So in this region we have calculated in some way what is a representative of this data, and that representative happened to be 4.2%. So when we're talking about here, we're just discussing how to interpret this tree. When we are going to make our own tree, we look at different things. How we got this 14.5, why not, why not 15.5, why not 16, and why we chose this 4.2. So that will come later when we discuss how to make this tree. right now we're just saying how to interpret this tree. So this is the region that is, so I can associate this with this part. So the second question is, the second part, if the hours worked is not less than 14.5. So now I'm skipping this part. So this part is being skipped from here to this. So I'm skipping this part and I'm going to the next question. So the next question is the hours worked greater than 29? So if the answer to this, are the hours worked greater than 29, if the answer is a yes, so this is a yes and this is a no. So if the answer is yes, it means I am referring to this part, because this is the part where we had greater than 29. So in this case, again, the representative is 2.5. So 2.5% efficiency or productivity we're getting for this. And next, if the answer is no, so if the first part was this, so it's not this part and it's not this part. If you are going to look at the third one, we're going to look at 23.5. So it's not this part and it's not this part. So next question, if it's greater than 23.5, if the answer is yes, it's greater than 23.5, so it means that we are referring to this region. So this corresponds to this region, because already we said that it's not in this part. So it's not in this part, because if it were in this part, we would have gone with the yes, and it was been 4.2% efficiency. So we took no greater than. So at the first instance we said it's not this part, so it's this part, and in this we have already said it's not greater than 29, so it's not greater than 29, so it's not this part either. So now we have this part and we are saying it's greater than 23. So if it's greater than 23.5, so it must be this part. So this is the data that is representing this part. So this corresponds to this portion, and then finally this corresponds to the remaining one, which is this. So you can see where we got the 100% value from. This is the 100% productivity or efficiency. So this is how you interpret the regression tree once you have a regression tree. And it's pretty simple to see which one is a better fit, if we use the straight line or if we are using a regression tree. So it's obvious that the regression tree is a much better representative of the data as compared to the straight line. So, but there's another question here. So this straight line was a bad idea. So what if somebody tells you, like, you don't need, why did you even put this straight line? If you ask me, and if you say that what's going to be the value at 20 hours, I can just make a line direct to the data. I don't have to have any line for that. I don't have to have a regression or a trend line for that. I can simply predict from the data. So if this is the value and I'm this is giving me 100% productivity, so why do I need this tree? I mean, it's so easy. I can just go directly to the data. And the answer to that question is yes, it is easy in this case, because there is only one attribute, hours worked. Now imagine a case where you have more than one attribute. So in this case, if you have more than one attribute, for instance this, so now it will no longer be straightforward, because now it's not a two-dimensional graph. Now it's going to be a 3-dimensional, 4-dimensional, 5-dimensional graph. So if you are looking at that, it is no longer going to be very easy to make a visual prediction of how you are going to get that value. So in this case, what we need to do is we need to have a regression tree. So that's why the regression tree is a better way to deal with this problem. And as we can see that we have here 3 different attributes. So the hours worked, the age, and the gender. And here we have the efficiency or the productivity, and these are the values, and there are other values as well. So this is just a representation of the data, not the entire data. So this is why we need the regression tree. Now we come to the main question. We know what regression trees are, we know how to interpret a regression tree, but how can we build our own regression tree? So for this, as we did with the decision tree, we need to have some, we need to make some decisions. So to make a decision tree, we need to make some decisions, and those decisions are that I have here 3 attributes. So the question is, these are the attributes, and this is the predictor. This is the prediction I need to make. So the first question I need to ask is, suppose okay, in this tree we have age is greater than 50. So the first question is, why 50? Why not 25? Why not 73? Why not 60? Why not 90? Why 50? So this is the first question. How to split, how to decide where to split. So this question is relating to this part. Where did you get this 50 from? The second question we need to answer is how to decide the output. So if we say age is greater than 50 and the answer is yes, we say the efficiency is 4%. And the second question is, where did you get this 4? Why not 10? Why not 20? Why not 2? So the answer to this is, where did you get this 4? And the final question here asked is, which attribute to split? So we chose age as the first attribute, as the root node. However, there are 3 different attributes. So my question is, why not hours worked? Why not gender? Why did you start with age? And so this is the third question of which attribute will become the root node. So if we can answer these 3 questions, we can make our own regression tree. And that's exactly what we are going to do in the next few slides. So let's come to the first question. So in this case, we are going to assume that we know which attribute to split, which attribute to use as a root node, and the question is how to split. In other words, we're not arguing that why age is the first attribute, we are arguing why 50, why did you split at 50? So let's try to answer this first question. How do you split? So let's take back our original data. So this was our data. Suppose I decide that I am going to split here where this value is, for instance, let's suppose 3. So this is 3. Oops. Yeah. So if I'm going to split at hours work is 3, this is what I get. On the left part, so the yes part, if it's less than 3, I only have 1 data point, and the value here is 0. So this is represented as the average value here is 0. And on the right side, I have a lot of data points, and the average of these values is 38.8. So this is the average, and so it goes somewhere around here. This is the average of all these values along the y-axis. So if I put this plus this plus this plus this, so on along the y-axis, I take their y-axis values and I just divide by the total number of data points. This is that 38.8. One thing you need to remember here is that in the branching nodes, this is a branching node because you are making a decision there. So this is a branching node and this is a leaf node. So in the branching node, you are taking the attribute which is here represented in your x-axis, while in the leaf node you are taking the value that the category or the value that is being predicted. So the simple thing is, if I use 3 over here, I get 2 averages. And the next question is, or the original question was, why did we use this 3? So to decide on which is the best value to use, we can make certain calculations. So if I use 3 over here like I did, so I have one data point over here and the rest of the data point on the right side. What I can do is I can calculate the sum of squared errors. It's also called the sum of squared residues as a result of using this split. So splitting at 3, if I use split at 3, so the average here is 0, so represented over here, and the average in this part is 38.8. So I can use the sum of squared errors. So if my 38.8 lies somewhere around here, I can calculate what's the distance between each point and this average value. So I can use this one, and then I can have this one, and so on. So for each data point I'm going to, which is shown over here. So all the data points are subtracted from the mean corresponding to that region. So there are two regions. This is region 1 and this is region 2. So in the first region the average is 0. So if this corresponds to the sum of square of the first region, so this belongs to R1. The value here is 0 and the average here is also 0. So 0 minus 0 squared. So this belongs to the first region and these belong to the second region. So the second data point is also 0, but in this case the average here is, as shown, 38.8. So 0 minus 38.8 square, and then I move on to the next data point, which is again 0. So I get this and I get this. So in this case, in the fifth data point, the value here is 5. So 5 minus 38.8, so which is this, and so on. And if I take the total, this sum of squared residues, I'm going to get something about, so this is 27,468.5. So this is the sum of squared residue or sum of squared errors. So if I calculate this value corresponding, so this is the value I get when I use 3 as a split. So hours work is split on 3. So I get this value. Now what I can do is I can try different values. So if I use 3 and then if I use all possible other values, and then for each value I can make a graph. So for hours worked equal to 3, I got around, so this value was around 27,468. So 27,468. This corresponds to the split where hours work is 3. So for different split I have different this sum of squared errors, and I'm going to choose the split which corresponds to the lowest sum of squared value. So this is that point, and this happened to be 14.5. And so this is why we chose in the original data set, in the original graph that we saw, the regression tree, we chose 14.5 as the split. So we choose 14.5 as the split because this corresponds to the lowest sum of squared error or lowest sum of squared residue. So if the answer is yes, we gave an efficiency value, and we don't know that what that value is, so I'm going to represent it as x. And that was the second part of making the regression tree, is estimating these values. And the third part was, choosing which attribute to use. But what we're trying to discuss in this slide is, so when I said hours worked is less than 14.5, I immediately made this into a leaf node and I gave the productivity or the efficiency of that. Whereas, so in this part, I am saying that this portion here is going to be represented by x. So this is x. But this one needs to be further split because, the difference between these values is quite high. So next I am going to use the same trick again. I am going to have another split, maybe over here. I can have a split over here, and then I can have a split over here, and find the sum of squared residue for this and the sum of squared residue for this. Obviously it's going to be lower in this case, and then I'm going to make my next split and then move on. So this is how the final tree is going to look like. If I continue doing that, I'm going to have 4 different leaf nodes. So 3 splits corresponding to 4 leaf nodes. So we have arrived at the original tree where the hours worked were less than 14.5, greater than 29, greater than 23.5. And a very good question is, why did I stop with this node as a leaf node, and this continued as a branching node? So I'm going to write it, so we're going to come back to this and we're going to answer this question. So let's say when to stop splitting. So we're going to, in this video, we're going to come back and we are going to answer this question, when to split this video. For the meantime, what we are going to do is, now that we have made this tree, we have made all the splits, we need to plug in this A, B, C and D value. So this is the region A, this corresponds to this part, B here corresponds to this part, C corresponds to this part, and D here corresponds to this part. So what the next step here is having a value that is representative of this entire region, and for that we use the simple average. So in this case we have 0, 0, 0, 0, 5 and 20. So 1, 2, 3, 4, 5, 6. There are 6 values. So 0 plus 0 plus 0 plus 0 plus 5 plus 20 and divided by 6, and this is going to give me 4.2, and this is how we arrived at this 4.2 value. And this is the average of 100 plus 100 plus 100 plus 100 divided by 4, which is this value, and then all this divided by 1, 2, 3, 4, 5, 6. So this is how we arrived at this value, and this corresponds to this part. So we have now figured out 2 things out of the 3 things. The first thing is how to split, how to get to this 14.5 and this 29 and this 23.5, and the answer to that is that you use the sum of squared error, and you take that split which will result in the least sum of squared errors. And so once you have that, you are going to take all the data points that belong to this region, so this is region A, and then calculate the average values. And if you remember, I said the splitting is done on the predictors or the attributes, and the leaf node correspond to the value of the predicted or the attribute that has to be classified or predicted. So we have answered 2 of our questions, how to get to this and how to get these values. Now we are going to go to the third part of the third question of how to make a regression tree. And for that we are going to have a look of some of this formula. If you remember, this was from a decision tree. So this was the entropy. This was the entropy of the entire data set. So entire data set, and this is after choosing an attribute. So this part, and if you subtract the entropy after and before, you are left with the gain. So this is the gain in entropy. That's what we did with decision tree. In regression tree, the framework or the idea is very similar. We are going to, instead of calculating the entropy, we are going to calculate the standard deviation of the entire data set. So this is the standard deviation of the entire data set, and then we are going to calculate the standard deviation reduction, which means the entire data set versus the standard deviation we get after choosing an attribute. And finally, if you remember, I said we are going to come back and answer the question of when to stop splitting. And so for that we have this coefficient of variation. This coefficient of variation is the standard deviation divided by the average or the mean multiplied by 100. So this coefficient of variation is what we will use to decide when to stop splitting. So the reason we stopped splitting in this case was that the coefficient of variation was less than let's say alpha, where alpha is a predefined value that we selected before we start making the regression tree. So if I say my alpha is, let's say if I say alpha is equal to 5, and then when I make this region, when I make this split at 14.5, I have this region, I take these 5 or 6 values, and then I'm going to calculate the average and standard deviation and then compute the coefficient of variation, and this coefficient of variation was s divided by x bar multiplied by 100. So if this value is less than alpha, which in this case is 5, that's why I decide not to go any further with this node, while for this case the CV is greater than alpha, and that's why we are going to continue the split. So that was the reason we stopped here and we decided to continue in this case. So let's take an example. So this is a data that represents these are the predictors and this is the target or the predicted value. So these are the attributes and this is the target. So we have outlook, temperature, humidity, and whether it is windy or not, and this is the values corresponding to these attributes. Now previously in the decision tree we saw that this was a play tennis yes or no. This was a category. In the case of a regression tree we are having real valued numbers, so how many hours are we going to play. So in this case what we can do is we are going to make, just like in the decision tree, we first of all computed the entropy of the entire data before looking at the gain. In this case we are going to calculate the standard deviation of this data. The standard deviation of this data is 9.2. So 9.2, this should end over here. So this square root is only for this part. This is the answer. So 9.2 is the standard deviation of the entire data without considering whether the temperature is hot or mild or cool, or the outlook is rainy or overcast, or humidity is high or normal, or whether it's windy or not. So without looking at any of these attributes, just on the target data, the standard deviation is 9.2. Now we are going to look at the attributes. So let's look at outlook as the first attribute. So in case of outlook we have 3 possible values, whether the outlook is sunny, overcast, or rainy. So this example corresponds to when the outlook is sunny, and then here we have overcast, and here we have rainy. So this we can compute the standard deviation of this part. So sunny standard deviation is, so this is the standard deviation we get corresponding to this part, and for overcast we have this, the standard deviation. So this is the standard deviation, and for rainy we have this part. So we have the count and we have the standard deviation, and now we can make a weighted probabilistic standard deviation. So if it is overcast and the number of data points is 4, so this is going to be 4 divided by 14 multiplied by 3.49, right? Then plus 5 divided by 14 multiplied by 7.78, and plus 10.87 and sorry, just put it at the end, multiplied by 5 divided by 40. So this is going to give us 7.66. So this is how we arrive at this 7.66, and this is the standard deviation that we get from using outlook as the attribute at the root node. So this is what we so after that we saw that the total standard deviation was 9.32. So 9.32 minus 7.66. So this here, this value is 9.32 minus 7.66, which is the standard deviation reduction. So this is how we got this value, and we can calculate similar for temperature, humidity, and whether it is windy or not. And from this we see that the highest reduction of the gain, just like we had information gain, the highest gain is 1.66. So outlook is going to be the root node. That's how we chose outlook to be the root node. And next, so if we choose outlook to be the root node, we have three possibilities: sunny, overcast, and rainy. So if it is sunny and whether it's overcast or rainy, in addition to the standard deviation and the average value, we also calculate the coefficient of variation. Remember that we use that for deciding whether we have to continue or not. So in this case, for instance, if our alpha was equal to 10, it means that we are only going to continue splitting if the coefficient of variation is greater than 10. So in this case, this is 8, which means no more splitting, and we are going to make it into a leaf node. So when I make it into a leaf node, what value do I put? I use the average value. So this is the average value that I'm using. In this case, it is 22. So 22 is greater than 10, this 10, and here it is, sorry, this is 28. And this is 22, which is greater than 10. So both these will expand as branching nodes. It means that we have already chosen outlook, so this is no longer available. We have to choose one of humidity, temperature, or wind. And to do that, we are going to repeat, we are going to calculate the standard deviation of this as it is, and then the standard deviation after we use humidity or temperature or wind, and then decide. So the final tree is going to look something like this. So I hope with this example it is clear how you make a regression tree. And if you have any question, you can write to me either in the comment section in this video or on your CMS, or you can simply email me, or we can discuss that during the interactive session we'll have later in this week. So in summary, regression trees are able to predict real values and not just categories, and they are very similar to decision trees. So instead of using entropy, we're using standard deviation, and we have similar gain, and we still have this problem of pruning and overfitting, just like we have in decision tree, and we are going to use similar ways to deal with that problem. And finally, both decision tree and regression trees can be used alone, or they can be used in ensemble. I said this in the last video as well. So it's a very powerful technique. Unfortunately, we cannot cover it in this course, but for those of you who will be using it based on the decision tree or a regression tree, you can look at what is called the random forest, and very simply it's just a collection of regression or decision trees that work together to increase the efficiency or effectiveness of the algorithm. And then we can use cross-validation strategies. We'll be discussing these in maybe the next or a couple of after a couple of videos what these strategies are. So you can read for further. You can look at few examples in these web links. So that's all for this video. Thank you.